Welcome you all, and today we will discuss some exercises which I have left in my previous talks, and we will see the solution of these exercises. So, before going to the exercises of all these, before going to the to prove or to solve these exercises, let me recall the definitions which and the results which we have already done. So you know that a collection of subsets of a metric space X is called a cover of X if X is equal to uh, if X is equal to the union of the G alpha, where G alpha is a subset of F. If each G alpha is open, then this cover is called an open cover, and this is finite, then it is called a finite cover. So, and so here you have a finite, then you have a finite cover, or if you have Y is a metric space and X is a metric space and Y is a subset of X, then the collection, this collection of subsets of X is called a cover of Y if Y is a subset of the union of G alpha. So then we have given the several examples and several definitions, and then finally the definition was the compact space. So a metric space X is said to be compact if and only if every open cover has a finite subcover. Okay, so that's the important thing. A metric space X is compact if and only if every open cover has a finite subcover. Keep in mind, in the reanalysis we know that a closed and bounded interval, is called compact, or a set is compact in the reanalysis. It is closed and bounded, but it is not true here. Here in the case we have a different definition which says that is metric space X is compact if and only if every open cover of X has a finite subcover. And then we have given several examples of a compact set or of a non-compact set. And we have proved that if Y is a subspace of X and then Y is compact if and only if every cover of Y by sets open in X contains a finite subcover of Y. Okay, so this is we have a result, and then every closed subset of a compact set is compact. This we have proved, and then we have given the remark that intersection of compact set is compact, after intersection of compact set is compact, and finite union of compact set is compact. And then we defined one finite intersection property. So a collection of subsets of X is said to have a finite intersection property if every finite subcollection of C has non-empty intersection. Okay, and then there is a characterization. We say that characterization of a compact set, we say that every metric space X is compact if and only if every collection of closed sets in X having finite intersection property has non-empty intersection. Okay, so this we have proved already, and then we have proved this exercise. Now let us come to the exercise. So the exercise is the first exercise is that let XD be a metric space, okay, such that every subset of X is compact. Keep in mind, the question is X is a metric space such that every subset of X is compact. Then prove that X must be finite. So every subset of a metric space is compact, then the space X should be finite. Okay, let's prove this one. So we can take we can start from, we can take an arbitrary point X. Okay, you take X is any element in capital X, and now since X, okay, you can you can remove the singleton set X. You can remove the singleton set X Okay, and then the set X, this is compact because this is a subset of X, which we are saying that every compact subset of X is compact. So from the set X, we are just taking out singleton set X, then this set is X. And we have proved that every compact set is closed. Okay, and therefore this set is closed. Okay, and hence the complement of closed set is open, and therefore the singleton set is open. Okay, so this way we can prove that it is open. Okay, so singleton set is open. Now you take because X is in capital X, so for each X in capital X we will have the singleton sets, and you take the collection of such singleton sets, and singleton sets are open. Here we have the singleton sets are open. So you take the collection of all such singleton sets which are open. What you will get? We will get the whole space. That is to say, the singleton sets okay, form an open covering of X. So the singleton set will form an open covering of X. And now since X is compact, so compact, okay, X is compact, so there must be a finite subcover. Okay, so there must be a finite subcover that is equal to x1, x2, xn of the cover this one. Then this finite subcover, because this is the finite subcover, so X must be a subset of the union of all these things, union of all these sets. So X is a subset of union of irons from 1 to n xi. Okay, but this is what? This is the xi is the singleton set. So this is equal to your the set x1, x2, xn. So X is a subset of x1, x2, xn, which concludes that X has cardinality at most n, and in particular X is finite. Okay, so this way we can prove that if every subset of a metric space X is compact, then X is finite. Now we have left, we have mentioned as a remark that any intersection or arbitrary intersection of compact sets is compact, and finite union of compact set is compact. Okay, so now we will prove the part B, and part A is left for you. Okay, so part B means we have to prove that any finite union of compact set is compact. Okay, finite union of compact set is compact. So let yk, okay, let k runs from 1 to m be a family of compact sets in a metric space X. So this is the finite family of compact sets in X. Okay, we will have to prove that the union of this family, which is equal to the union of k runs from 1 to m yk, the union of this family is compact. Okay, so for that we have to prove that every open cover of this has a finite subcover. So let us take f is equal to g alpha. Alpha is in lambda, and lambda is any index set. So let f is equal to g alpha be an open cover of the union of yk. Okay, by sets open in X. Since each yk is compact, there exists a finite subset jk, okay, jk of lambda such that yk must be in the union of g alpha i's and alpha i's in jk, and k runs from 1 to m. This k runs from 1 to m, and therefore the union of yk, union k runs from 1 to m yk, Okay, so this union must be a subset. So because here this for each yk it is in this union. So if you take the union of this one, this must be in this union. So this is a subset of this one, where j is equal to the union of jk's and k runs from 1 to m. This is a finite subset of the index set lambda, and hence every open cover, okay, this was every open cover of union of yk by sets open in X has a finite subcover, and therefore by this lemma, Y is compact if and only if every open cover of Y by sets open in X has a finite subcover. So by using this lemma, we can prove that the union of Yk is compact. So this way we can prove that the finite intersection of open sets is open, and similarly you can prove the arbitrary union of open sets is open. Now we have another exercise. We say that prove that a metric space X is compact. A metric space X is compact if and only if every family of closed sets in X, every family of closed sets in X with empty intersection, okay, has a finite subfamily with empty intersection. So this is nothing but you can see that it is the complement of the finite intersection theorem. Okay, what we have? We have to prove this one. So here is the theorem is that let X is compact if and only if every collection of closed sets having finite intersection property. Having finite intersection property means every finite collection, okay, has non-empty intersection, okay, and every finite intersection property then has every collection of closed sets in X having finite intersection has non-empty. So the whole collection has a non-empty intersection. Now here is we are reversing this one. We are taking here, instead of taking any collection of closed sets having the property that any finite intersection is empty has the empty intersection. So that is the, you can say that that is the complement of this theorem, which is this exercise. So let X be a metric space. Okay, so prove that a metric space X is compact if and only if every family of closed sets with empty intersection has a finite family with empty intersection. Okay, little bit change. So here you can see that let X be a compact metric space and C alpha be a family of closed sets in X such that the intersection of C alpha is equal to empty. Okay, so we are assuming that X is compact and every family of closed sets with empty intersection. So we have a family of closed sets with empty intersection, and then we will have to prove that this has a finite subfamily with empty intersection. Okay, so taking the complement from here, you take the complement. So what you will get? The complement of empty set is equal to whole space, and the complement of this set, they complete the intersection C alpha is equal to union of C alpha and the complement of this set. So you will get this one. It means what? It means that X is equal to union of C alpha C, complement of C alpha, but C alpha is closed. So it means that this set C alpha C is open. So this is, you can see that X since X is equal to this one where C alpha is open, we can say that the family of C alpha C, okay, where alpha is in lambda, is an open cover of X. Okay, so since this is the complement of the closed sets. Okay, so this is your open, and therefore F is equal to C alpha. C alpha is in lambda is an open cover of X. So this way we have this is your open cover of X. Now, since X is compact, okay, since X is compact, there exists a finite subcover capital C of cover F such that C of alpha 1 C, alpha 2 C and so on, they are the element of X such that the union of these elements must be equal to X. Okay, and now you take the complement. So if you take the complement of X, you will get the empty set, and the complement of this is equal to this one. So this is a finite family. This is the finite subfamily with the empty intersection. So this way we can prove the one part. Let us prove the other part, the converse part. Okay. To prove the converse part, let us assume that the hypothesis holds. Hypothesis holds means that every family of closed sets with empty intersection has a finite subfamily with empty intersection. Okay, and then we will have to prove that X is compact. Okay, so we have to prove that X is compact. X is compact means we will have to consider any open cover of X and prove that it has a finite subcover. So let F is equal to G alpha, and alpha is in lambda, be an open cover of X. Okay, and then we will prove that this open cover of X has a finite subcover. So because we are assuming that this is your open cover of X, okay, so the X must be equal to the union of G alpha. Okay, so this is holds good, and then take the complement both the side. So if you take the complement here, complement of X is your empty set. Okay, the complement of this, okay, this the complement of union of G alpha must be equal to the intersection of G alpha complement. Okay, so we have this. So this is what it means that G alpha C, this is your family of, this is your a family of closed sets, but G alpha was open, so the complement is closed set. So G alpha closed set with empty intersection. So this family is this family of closed sets with empty intersection, and now by hypothesis it has a finite subfamily with empty intersection. So so this is non-empty, thus this is a family of closed set with empty intersection. So by the given hypothesis there exists a finite subfamily. Okay, finite subfamily is G alpha 1 C, G alpha 2 C, G alpha n C, such that the intersection of all these sets must be empty. So you take the intersection, I runs from 1 to n, G alpha I C is equal to empty. Okay, and now you take the complement of this. Okay, take the complement of this both the side. So if we take the complement of this both the side, here you will get the complement of empty set is equal to whole space, and the complement of this is equal to the complement of this union I runs from 1 to n and the complement of this. So now the complement of the complement is the same set. So for example, if A is a set, then the complement of complement is equal to A, and therefore we will have this one. So this is the union of this, okay. So this is equal to X. This is equal to X. So it means what? It means that this G alpha i's, So, G alpha 1, G alpha 2, G alpha n. Okay, this is a finite subcover of F. Okay, and hence X is compact. So, this way we can prove that the set X is compact if every family of closed sets with empty intersection has a finite subfamily with empty intersection. Okay, take next exercise. The next exercise we take let Cn, n runs from 1 to infinity, be a sequence of non-empty closed subsets of a compact metric space X such that Cn plus 1 is a subset of Cn for each n. Okay, then prove that the intersection is non-empty. Okay, so this we have to prove. Let's see what is the meaning. Meaning is that here is first Cn plus 1 is a subset of Cn. So means that C1 contains C2, C2 contains 3, and Cn contains Cn plus 1 and so on. So this is a nested sequence of closed subsets in a compact metric space X. Okay, so this is a closed subset in a compact metric space X. So this is now then the collection this satisfies the finite intersection property. Okay, you can prove, you have to prove that this, because of this it satisfies the finite intersection property, and then by theorem this, okay, a set X is compact if and only if it has a finite has non-empty intersection. And therefore, the intersection of this finite intersection of Cn is empty. So, this way we can prove that this is exercise. Now, we have the final next exercise and that is the last exercise in this section. So, that is let X be a compact metric space and chi X is equal to X cross X minus 0 XX. You see that you take X cross X and you remove the diagonal elements. So, we remove the diagonal elements X cross X, removing the diagonal where diagonal is removed. Okay, so we are removing the diagonal element. Then prove that chi X is not compact. Okay, so it means that first let us take here is if you are considering the real line. Okay, so can you say that suppose if you have a real line, this is your real line R, and remove this is your 0, remove 0 from this real line, that is to say your R minus this. Can we say that this is compact? If we remove the 0 from R, can we say that R is compact? First, we have already seen that the whole R is not compact. Okay, because we have seen that there is a open cover of R which does not have any finite subcover. Okay, and in the real line, the set R must be closed and bounded. Okay, in the R, the set be closed and bounded. But this set, if we are removing this one, it means what? It means that you are considering minus infinity to 0 open interval union of 0 to infinity. So, we are removing 0, but this is your open, this is your open. So, it is not closed set. So, this is not closed and therefore, this is not compact. And the same thing is we can see that if we are taking this is in R2, okay. So, if you take this is in R2, for example, you have this is your So you can take x x. So x x. Okay. So diagonal elements. Okay. So you can take diagonal elements. You can remove. So you remove this diagonal element from the x, from the R2, then check whether this is a compact metric space or not. Okay, so for that we can give you again as a hint that consider the closed interval 0, 1 and check the properties of this. Okay, so just you check the closed interval 0, 1, so x is equal to 0, 1 and this one, and then you will can prove that x is not compact. Okay, so here is I stop this exercise talk. In the next talk we will see some other exercises or some MCQs. Thank you very much.